Okay, so again, I've got my ammeter and I've got my voltmeter. And then there's two different plugs here, and one of them is alternating current and one of them is direct current. Normally, well, not normally, in the United States and actually in most of the world, we use alternating current. Alternating current is a bit safer and it's easier to get the current to travel a very long distance with alternating current. Direct current is a little more dangerous and harder to get it to transfer. However, direct current is what batteries produce. So if you think about, if you learned in chemistry about batteries, and a battery is these layers of like different kinds of metal and cardboard, and then you put it in acid and it makes current flow. And that current's just going to flow in one direction all the time because of the chemical reaction that's happening. Again, that's direct current. With alternating current, what happens is the way that we produce current is with a generator. And a generator is something that spins like a hand crank or like a hydroelectric dam, like you have water flowing over a turbine, and that spinning creates the current. What happens when you use something that spins is that we're going to learn about this later, but there's this thing called a split ring commutator, and it causes the current, the way that it's set up, it causes the current to flip direction every time the generator spins. Actually, it flips twice. It flips every half turn. So what ends up happening is with a plug, on the two sides of a plug, they actually flip back and forth from positive to negative. In the United States, it's our cycles are 60 hertz or 60 cycles per second. So the positive and the negative flip back and forth 60 times in 1 second. A couple other things about plugs in the US. So see how one side is fatter than the other? The fatter side is the positive terminal and the skinnier side is the negative terminal. And if I had a third prong, that would be ground. The ground of an outlet is supposed to be literally hooked up to the ground. And the way that they do that is they take a wire and they hook up the wire from that ground to the plumbing. I am here to tell you, though, that if you do it yourself and you don't hire a licensed electrician, it is possible to do it wrong, and that is kind of dangerous. Anyway, okay, so let's see. So we've got this power supply, and then the next thing that I have is I have a circuit. So let's see if I can make this look good. So a circuit is a circle. I don't know if you guys can see that this is a closed loop. In order to have the light bulb turn on, which I'll do in a moment, we have to have a closed loop. So, ta-da! Ooh, that looks pretty cool on the Zoom. Here I've got a switch. Let me put this down a little bit. Here I've got a switch, and if I open the switch and break the circuit, then the light bulb goes out. So again, in order for this whole thing to work, I need a power supply with voltage, I need a closed loop, and this light bulb is a resistor, and what it's doing is it's taking the voltage, which remember is energy per unit charge, it's taking that energy and it's dissipating it. And with a light bulb, energy is dissipated by heat and light. Many of the appliances in our homes, like if I think about a toaster, or I have an electric stove, a hair dryer, electric blankets, all of those just basically are dissipating energy as heat or heat and light. Other things run motors and they're doing work. So that's fun there. So this is what my circuit looks like. Notice also the similarity between the word circuit and the word circle. Circuit, circle, not a coinky dink, okay? That's basically means the same thing. And also as I turn this up, you can see the voltage is going up and the current is going up, but it's going up only a little. The current here is pretty low. which is good because this thing is built for me to play with my hands, and I can touch it and I'm not getting electrocuted, nor am I ruining my computer. That's good day for me. Because the resistance of my body is much more than the resistance of these wires. So the electricity wants to just keep going through the wires. It's easier for it to go through the wires, so it's not going to go through ground through my body. Thank goodness. Ooh, that's really hot. Had to bring you guys a little bit of excitement. You're going to get a blister. Holy bananas, that's hot. Okay, well, good to know. Learn something every day. I don't think this light bulb was rated for that much voltage. Okay, we're just going to put this friend over here. And let's see. I have shocked myself. It's bad. Yeah, that's going to leave a mark. It's not a good idea to play with a power supply like that near a sink, because the sink is such a good conductor to ground that I have touched a power supply and a sink at the same time, and I've gotten a really bad shock doing that with an audience of students. So that was not my finest moment. Okay, so when we draw a picture of this, like I love to draw, so like I would love to draw like a 3D rendering of there's the power supply, and then I'm gonna have like the light bulb, like this would be fun, right? And then the switch. But we don't have all day to draw all these pictures. So what we do instead is, for a power supply, we draw a long line and a short line. And the long line is the positive terminal. Then to draw a switch, you draw a gap like that, and it's like a door, kind of. Then for a generic resistor, it's just a squiggly line. And then we close the loop. So this is how I would draw that circuit that I just showed you. And again, this would be the power supply, the switch, and the resistor. Okay, and then there's a couple of things that I can measure about the circuit. One thing that I can measure is the current, and one thing that I can measure is the voltage. So now I need to talk a little bit about what is current and what is voltage. So current is charge per unit time. And the symbol for current is an I. Now that's kind of annoying, right? Because current starts with C. But we already used C for capacitance. By the way, I don't know exactly who decided all this, but here we are. Like many things in the world, here we are, the result of whatever happened in the past. And so the unit for current is I, and it's measured in amps, which is short for amperes, which actually, if you know your French, it's got an accent grave on the E, because it's named after, what was his first name? I think it was Andre Ampere, a French physicist. Anyway, in America, we usually shorten that and just say amps. And it's equal to charge, which would be Q, which is measured in coulombs, over change in time, which is seconds. So an amp is a coulomb per second. And an amp is a coulomb per second. It's how much charge is moving per unit time. And here I can kind of call back to what we measured, or what we learned about fluid flow. We kind of want to now think about current flow as kind of like a fluid. Like, how fast is it going and how much is there? Is it a little trickle of charge, just like a little teeny stream, or is it like a huge deluge of charge? It's the current that actually causes injury to humans. It's the current, not the voltage. And the reason for that is that the current is going to carry that energy energy per unit, let me back up, sorry. The electrons are energy carriers. So we want to think of the electrons as energy carriers. So the more charge that is flowing, the more energy they're going to carry. And if that energy is going through your body tissues, it gets dissipated as heat, and it causes burns, which I already knew, so I didn't really need a reminder of that. But I'll probably be running into lots of things today because it's kind of a day. Okay, let's see, what do we got here? Yeah, that's pretty good. Okay, another thing we know about, I think I've got some room over here, is we know about voltage, which is also called potential difference. And what we would say is that there is a voltage across this power supply. If it were plugged into the wall, most wall circuits have a voltage of 120 volts. When I've got a little power supply like that, it's much smaller than that. So what did I turn it up to? I'm just taking a peek here. Oh, it's still on. I had it turned up to like 10 volts. The round batteries that you put in stuff, like a double A, a triple A, a C, and a D battery, all of those are 1.5 volts each. And if you, let's see. Oh, I was gonna grab my other. I don't know if you guys still have your graphing calculators handy, but here's my graphing calculator, and here's my 4 batteries. These are wired so that all 4 of those batteries are in series. They don't look like they're in series because they make it so it's easy for you to pop them in the thing, but they're really set up like this. So that all together, it's providing 6 volts to the calculator. And if you can read the fine print really, really small, it'll tell you that somewhere, but I can't see or read anymore because my eyes are going out the window. Okay. Okay, so what else do we know about voltage and potential difference? We know that voltage is energy per unit charge. So it's joules per coulomb. So we've got energy per unit charge, and then we've got coulombs per second, and those two things together determine how much energy is flowing through the circuit. And then that energy is, again, is either dissipated through the resistor or the resistor uses it to do work. Some other fun facts, and then I should probably pause and see what questions you have. In the United States, we model current as positive charge flow. So in this circuit, I would say that the direction of the charge flow, I would say it's coming out of the positive. I would say the protons are moving. They're not really, but that's how we do it here. I'd say the positive charge flow is moving this way, and I would say it's going around the circuit counterclockwise. That's called conventional current in the United States. The rest of the world does not use conventional current. They model charge flow with a negative charge. So they would say that the current is flowing clockwise, but it's negative charge flow. Why do we do this? I probably should study it again, but to the best of my knowledge, it does go back to Ben Franklin, who assigned a charge of positive to the spark that he saw when he flew a kite in a thunderstorm to show that lightning is electricity. Okay, I will pause and let's see how we're doing.